Hello everyone, welcome to all of you in my lecture today. So here I'm going to teach the topics of evaporator in heat transfer, and I will be going through the concept of batch evaporations and the continuous evaporator, and as well as I will be deriving the mass balance and energy balance for the evaporator, and we'll be discussing about the steam economy and the capacity of the evaporator in this lecture. And in the subsequent lecture, I will be discussing about the difference between the single effect evaporator and multiple effect evaporator, and effect of the boiling point elevations in the capacity and stream economy. Okay, so let's start for the topics today, that is the evaporation. uh, you can see on my screen that the evaporation process is a unit operation which is used to increase the concentration of solute in the solution by removing a portion of solvent through supplying heat, right? So now this is a unit operation. So definitely we'll need an equipment to carry out this unit operation. So the equipment in which the unit operation is taking place is called as the evaporator, right? So we have seen the definition of this particular unit operation, and now we'll come to the modes of operation, like classification of evaporator. Here I am discussing a classification of evaporator. So generally there are two types of evaporator in our syllabus. First one is, my dear student, that is batch evaporator, and the second one is, that is continuous. So now, where will you use batch evaporator and where will we use the continuous evaporator? The question arises here. So generally, batch evaporator is for the experimental purpose, that experimental purpose or a small scale level production. But when it comes to the continuous evaporation, when it comes to the industry, that this will be used for the industry, or it is used for large applications, right? So generally in batch evaporator, what happens? There will be a pan only, and here your solution will be placed over here. Now we'll be supplying heat over here. So this the water will be getting evaporated, and this solution is getting concentrated in terms of solute. Okay. So after a particular time in this batch evaporator, you will get a concentrated solution. Now coming to the continuous evaporator, this is our main aim to study in this particular lecture. So I'll be coming to the next slide in the continuous evaporator. So let's draw the diagram for the continuous evaporator. So the equipment will look like that, right? Diagram is not very accurate, but you can understand the thing. So here we'll be supplying the feed, okay, and that feed will be either in kilogram per hour if we take the SI unit. So here after evaporation, a part of this component will come as vapor and the bottom product will coming as a liquid, and here the unit will be also kg per hour, and here the unit will be also kg per hour. So when we you will be solving the problem, definitely for the material balance problem, you'll have to make the unit very correctly. Now, here, since this is an evaporation, so feed is going into the evaporator where vapor and liquid is coming out. So definitely we'll have to supply the heat. So the heat is being supplied by this steam jacket, right? So here, a steam is going, the, mass flow rate of steam is as, that is in the kg per hour, right? And the latent heat of vaporization of that steam, that is lambda s. Now, the temperature inside this evaporator will be T, that is the solution temperature, right? Feed is being subjected at T naught temperature. The initial temperature, I am assuming that feed is T naught. So I am assuming T naught is equals to initial temperature of feed, right? F is equals to feed flow rate, and S is equals to stream flow rate. Lambda S, that is equals to latent heat of vaporization of steam, right? And I am assuming Cp of feed, that is heat capacity of feed material, right? So all these things will be in the SI unit. So heat capacity is kilojoule per kg Kelvin, right? Here it will be equals to kilojoule per kg. So now coming to material balance, right? So here you can see the feed is going and vapor and liquid is coming. So when we apply the material balance, overall material balance, that is overall material balance. So can I write, my dear student, F is equals to vapor plus liquid component? That will be our equation first. So here we have written F is equals to L plus V. That is our equation first. Now, since water is being evaporated, since water is being, so solute will be same. So can I make material balance for solute? That is the neutral component. You can call it as a neutral component because it's not going to be evaporated, because our main aim is to concentrate the solution, right? So you'll have to evaporate the water, and the component concentration of solute in the water will be increasing, right? So material balance for solute. So if here in this diagram you can see, if this is our evaporator, here if feed is going and mole fraction of solute in feed is XF, and here if it is L and here it is V, is one very important thing that you need to understand over here is, since feed in feed solute will be there, and here in V, here also solute will be there, but in, sorry, I made one mistake here, let me correct it. uh, Here it will be vapor and here it will be liquid, sorry for that. uh, Here it will be, my dear student, vapor, and here it will be liquid. So here in vapor, there won't be any solute. Ideally, if we take, right? Because here only water vapor will be there. So here water vapor will be there. So no solute is here. No solute will be there, right? So if we talk about mole fraction of solute here, that will be 0. And here it is mole fraction of solute is, I am assuming it, XL, right? So if we apply the solute balance, so can I write F into XL, that is equals to L, sorry, F into XL, uh, just wait 1 second. Yeah. So what I was discussing here, uh, that is, sorry for that mistake. Uh, Here our F was there, and here already explained, that is V, and here it will be L, right? So coming to here, mole fraction of solute was XF. Here mole fraction of solute, I have told you, that is equals to 0, and here mole fraction of solute is XL. So first material balance, overall material balance is equals to F plus is equals to V plus L, that is equation first. And now we'll apply solute balance, F into XF that is equals to V into, that will be 0 plus L into XL, right? So here can I write F into XF, that is equals to L into XL. That is equation second. This equation is very, very important equation. So from here, we'll get the relation between F by L, that is equals to XL by XF. So in the problem, sometimes you will be given that F value, XL value, and if it is telling that solute is getting concentrated from 10% to 50%, right? So here 10% to 50% mean, that is, my dear student, XF, that is equals to 0.1, and that XL. So up to 50%. So here it will be the solution, right? Here you will see the solution. So that XL will be like that XL is equals to 0.50. So here if you are getting F, if some F value will be given in the problem, you are getting you will be given XF and you will be given XL. So you can calculate value of L, and from there you can substitute this value of F and L here, and you will be getting the value of V. And after sometimes I will be letting you that V is called the capacity of the evaporator, right? So I think up to this, all the concept is very clear, that material balance and individual solute balance I have done right here. Right. Now I will be coming to the energy balance, right? So it's also very important thing. Most of the time, you will be getting the numerical on the energy balance in the gate examination. So it's very important that you'll need to understand that energy balance equation. So if this is our evaporator, right? So I mean, mostly energy balance is also connected to the material balance. You'll have to use that material balance concept over here. So here, if it is our feed is going, and uh, or we will supplying a steam through this coil over here. So if it is F, mole fraction of solute in feed is V. If it is V, if it is L, and it is XL, right? So, my dear student, now what we'll have to understand, if the uh, uh, enthalpy of that liquid is HL, here enthalpy of that vapor is HB, and if enthalpy of feed is HF, right? So, and latent rate of vaporization of steam is S, and mole flow rate of steam is S, right? So, if we talk about the energy balance, so can I write here F into HF, that is equals to uh, sorry, F into HF, that directly here I am writing one thing, try to understand. Basically, when we do the energy balance, we write what? Energy in, and that is equals to energy out, that at a steady state. At a steady state condition, where there is no accumulation of energy. There won't be any accumulation of, no accumulation of energy. So energy in will be equals to energy out, right? So how can we write the energy in? So energy in is coming from feed as well as steam, and this energy V and L is leaving. So can I write F into HF plus S into lambda S, that is equals to L into HL plus V into HB. That is our equation third. I think up to this, it's very clear that how I am writing this energy balance equation over here, right? So our energy in will be this part. This is our energy in, and our energy out will be, this will be our energy coming out from the evaporator, right? So now when we talk about the material balance, can I write V is equals to, my dear student, F minus L? So now if we substitute V over here, so can I write F into HF plus S into lambda S, that is equals to L into HL plus V we can write F minus L into HB, right? So again, we'll proceed this derivation further. So can we write F into HF minus F into HB plus S into lambda S, that is equals to L, and can I write, my dear student, HL minus HB, right? So now can I further proceed here? That is F, can I write HF minus HL plus S, that is flow rate of steam, into lambda S, that is equals to L. So that is here HL minus HB. So can I write F? I can write, if I am assuming Cp of feed, that is equals to Cp of liquid, that is equals to Cp. If heat capacity is constant, if heat capacity is constant, so can I write, my dear student, Cp Tf minus T reference minus Cp TL minus T reference, right? Plus S into lambda S, right? S into lambda S, that is equals to L Cp. So here I have done one mistake in, so we are writing here F into HF, right? So yeah, so we can write here Cp uh, TL minus T reference minus HB, that is Cp TB minus T reference. Okay, so now let's proceed further. So we can write now, or we can directly write here in this way. That is equation 4. Now further we can also write, if that depends upon what is being given in the problem. If HL or HB is given in the problem, lambda S is given, HF and HL is given, so you can use this equation. Or if heat capacity is given, then you can use this equation, right? So now next coming another thing, if it is given. So already we have written F into HF plus S into lambda S, that is equals to B into HB plus L into HL, right? So can I write here now F into HF plus S into lambda S, that is equals to, my dear student, B into HB plus F minus B into HL, right? So can I write F HF minus HL plus S lambda S, that is equals to B HB minus HL. So can I write F Cp T reference minus T, and if here I am assuming Cp of feed is equals to Cp of liquid is equals to Cp, means heat capacity is not going to be changed. So can I write, my distance, Cp TL minus T reference plus S into lambda S equals to V into lambda V, since lambda V is equals to enthalpy of vapor minus enthalpy of liquid, right? So can I write here F, that is Cp, sorry, here I have done one mistake. Uh, that will be equals to, uh, here it will be T feed minus T reference. So you can write here, that is T feed minus TL. That TL is equals to T, I am directly writing, right? Plus S into lambda S, that is equals to V into lambda V, right? So Now, what we can write, it's very in a simplified way, that depends upon the conditions. If H, that if lambda latent it, just like I am assuming here, try to understand. Here, if it is our evaporator, if it is feed and this steam is going S1, and here it was V and it is L. So this temperature is T. So in previous slide I am writing TL is equals to T. Okay. At this particular temperature, the water, I mean the solution will be boiling, right? So that equals to, you can write F into Cp T of feed. Here feed is supplied at a temperature of T feed, Tf minus T, that temperature T, plus S into lambda S, that is equals to V into lambda V. So can I write S into lambda S, that is equals to V into lambda V minus F Cp Tf minus T. So try to understand one thing. So definitely we are trying to supply heat to the system so that the temperature will be increasing. So definitely that T will be greater than Tf here. Okay. So here I am assuming T will be greater than Tf. Why? Because feed is coming to the lower temperature as compared to T. Why? Because we are supplying heat through this steam. Okay. So that's why this is the work of the evaporator, that will be supplying the heat through the steam, and it will, reach to the boiling point of the solution, and the water will get evaporated, and we'll get the concentrated, right? So you can write S into lambda S is equals to F into lambda V plus F Cp T minus T of feed. So this is very, very important energy balance relation for our evaporator, right? So if unit is given, S will be in kg per hour. This lambda A, which is latent heat of vaporization, V will be in kg per hour again. F will be in kg per hour. Cp will be in kilojoule per kg Kelvin, like that. Okay. So this is very important relation for our energy balance. Now coming to, we have derived S into lambda S, that is equals to V into lambda V plus F Cp, right? And that is equals to T minus T of feed, right? So if any numerical is coming by from evaporator, this very important relation is required for the solution of that problem, right? So now we are talking about this particular stream, right? Because we are supplying this steam, okay, here with latent of vaporization is S. So there must be an area of coil, right? There must be an area of coil, and so steam is supplying at a temperature of Ts, and here the temperature will be T, right? Here the temperature will be T, and this steam will be a temperature of T. So what will be Q? Heat duty of this particular steam jacket, that is equals to what? Overall heat transfer coefficient multiplied with area into delta T. Delta T is equals to what? That is equals to minus Ts minus T, and that will be equals to that flow rate of steam multiplied with latent heat of vaporization. That will be the heat duty of this uh, uh, coil, heating coil. So that is equals to my dear student S dot multiplied with lambda S. So can I directly write S dot lambda S, that is equals to UA delta T, that is equals to V into lambda V plus F Cp of feed T minus Tf, where delta T, that you will have to remember, that is equals to Ts minus T, and this T will be T saturation, sometimes it you can see. So right, so this is the energy balance. So, and here lambda is equals to latent heat of vaporization of a steam. Here I am writing U is equals to overall heat transfer of coil, that is heating coil. A is equals to area of heating coil, and that Ts is equals to temperature at which a steam is being supplied to the evaporator, right? So I think hope up to this the concept is very clear. Now, one very important concept that arises over here is the capacity and of single effect evaporator. So actually, I'm dealing with the single effect evaporator right now in this lecture. So I'm defining one parameter, that is capacity. Single capacity of single effect. So my dear student, already I have discussed so many times this diagram. Now this picture is coming in your mind that we will be supplying feed over here, and here the vapor will be going, and here this liquid will be coming, right? And here there will be a steam jacket through which a steam will be coming, right? Having latent heat of vaporization ST, and here the temperature of this evaporator is T, and here feed is supplied at a temperature of TF, right? So here that is XL, so XB will be 0 here. Feed of, that is mole fraction of feed in the solute in the feed, right? So we'll have to define the capacity. So the capacity is defined as kg of water evaporated per hour from the evaporator, right? So this is the definition of capacity. So now we can understand that what is water vapor. So the value of that water vapor is V. So directly we can write that capacity will be V, right? So if in the problem you need to calculate the capacity V, so capacity of evaporator, then you can directly calculate that is V. So how will you calculate the V? First, you will apply the material balance F is equals to L plus V. That will be your equation first. And next is that is solute balance, that is F into XF. That is equals to F into XL plus V multiplied with 0, right? V multiplied with 0. So from here you will be getting a relation F into XL is equals to F into XF, that is equals to L into XL, right? So from here, if F, XF and XL is given, you can calculate L. And so from here, you can calculate V is equals to F minus L. That will be your capacity of single effect evaporator, right? I think up to this, it's very clear now. Uh, now, hope I think I tried my best to let you understand all this concept of material balance and energy balance for the single effect evaporator. Now, in the next lecture, I will be dealing with the effect of boiling point evaporation, sorry, boiling point elevations in the uh, on the capacity as well as steam economy. So, in the next lecture, I will be discussing about the steam economy and as well as the effect of boiling point elevations of single effect evaporator. And next, I will be dealing with the multiple effect evaporator and will be comparing with the capacity and economy of single effect evaporator and multiple effect evaporator. Okay. Okay. Thank you and all the best.